Hello and welcome. In this video, we will explore the fundamental concepts of parallelism in vectors, a key topic in IB mathematics analysis and approaches higher level. By the end of this session, you will be able to: first, define and identify parallel vectors using scalar multiplication. Second, understand and calculate unit vectors. And third, apply these concepts to prove that 3 points are collinear. These skills are essential for solving a wide range of problems in vector geometry. Let's begin with our first objective, parallelism. Two non-zero vectors are parallel if and only if one is a scalar multiple of the other. This means that if we have two vectors, let's call them A and B, they are parallel if we can find a scalar, k, such that vector A is equal to k times vector B. The scalar, k, can be any real number, positive or negative, but it cannot be zero. If k were zero, vector A would be the zero vector, which has no direction and therefore cannot be parallel to anything. Visually, this means the vectors point in the same or opposite directions. If k is positive, they point in the same direction. If k is negative, they point in opposite directions. This relationship also tells us something about their magnitudes, or lengths. The magnitude of vector A is equal to the absolute value of the scalar, k, multiplied by the magnitude of vector B. The absolute value is crucial here, because magnitude is always a non-negative quantity. So to recap, two vectors are parallel if one is a scalar multiple of the other, and this scalar relationship also governs the relationship between their magnitudes. Let's work through an example to see how this is applied. This is similar to example 25 in your notes. We are asked to find the values of r and s, given that vector A with components 2, minus 1, and r is parallel to vector B with components s, 2, and minus 3. Since the vectors are parallel, we can write the equation A equals k times B for some scalar k. Substituting the components, we get the vector equation. The vector less than 2 minus 1, r greater than equals k, times the vector less than s, 2 minus 3 greater than. This single vector equation gives us a system of three scalar equations, one for each component. From the first component, we have 2 equals k times s. From the second, minus 1 equals 2k. And from the third, r equals minus 3k. We can solve this system. The second equation, minus 1 equals 2k, only has one unknown, k. Solving for k, we find that k is equal to negative 1/2. Now that we have the value of k, we can substitute it into the other two equations to find s and r. For the first equation, 2 equals negative 1/2 times s. Multiplying both sides by minus 2 gives us s equals minus 4. For the third equation, r equals minus 3 times negative 1/2. This simplifies to r equals 3/2. So by using the definition of parallel vectors, we found that s equals minus 4 and r equals 3/2. This demonstrates how to use the scalar multiple relationship to solve for unknown components. Now let's move on to our second objective, unit vectors. A unit vector is a vector with a magnitude of 1. It's a vector that tells us a direction without specifying a length. We often denote a unit vector with a hat, like a hat. How do we find a unit vector in the direction of any given non-zero vector, A? We divide the vector, A, by its own magnitude. This process is called normalization. The formula is a hat equals 1 over the magnitude of A times the vector A. Let's verify that this vector has a magnitude of 1. The magnitude of a hat is the magnitude of 1 over A times A. Using our property for scalar multiples, this is the absolute value of 1 over times the magnitude of A. Since it's positive, this simplifies to 1 over times, which equals 1. So it works. Unit vectors are incredibly useful. For example, if you want to create a vector of a specific length, k, in the same direction as A, you simply multiply the unit vector a hat by k. So a vector b of length k in the same direction as A is given by b equals k times a hat. If you want a vector of length k in the opposite direction, you multiply by negative k. This gives us b equals negative k times a hat. This is a powerful tool for constructing vectors with specific properties. Let's apply this to an example. This is similar to example 26 in your notes. We need to find a vector, b, that has a length of 7 units and points in the opposite direction to vector a, which is less than 2, minus 1, 1 greater than. Our strategy will be to first find the unit vector in the direction of a, then reverse its direction, and finally scale it to the required length of 7. Step 1. Find the magnitude of vector a. The magnitude of a is the square root of the sum of the squares of its components. That's the square root of 2 squared plus negative 1 squared plus 1 squared, which simplifies to the square root of 6. Step 2. Find the unit vector in the direction of a. The unit vector a hat is 1 over the magnitude of a times a. So a hat is 1 over the square root of 6 times the vector less than 2 minus 1, 1 greater than. Step 3. Construct vector b. We want vector b to have length 7 and be in the opposite direction. So we multiply our unit vector by minus 7. This gives b equals minus 7 over the square root of 6 times the vector less than 2 minus 1, 1 greater than. We can leave the answer in this exact form, or we can distribute the scalar. Distributing the scalar gives us the vector b with components minus 14 over root 6, 7 over root 6, and minus 7 over root 6. This vector has the correct length and direction. Our final objective is to use these concepts to prove that 3 points are collinear. Collinear points are points that lie on the same straight line. Imagine 3 points, A, B, and C, on a line. The vector from A to B, which we write as AB vector, and the vector from B to C, BC vector, must be parallel. So, the condition for collinearity is that the vector AB vector is a scalar multiple of the vector BC vector. That is, AB vector equals k times BC vector for some scalar k. This proves they are parallel. But parallelism alone isn't enough. For example, 2 parallel lines have parallel vectors, but the points on one line are not collinear with the points on the other. The crucial second part of the proof is to show that the 2 vectors share a common point. In our case, both AB vector and BC vector share the point B. Because they are parallel and share a point, they must lie on the same line. This 2-step process is the standard method for proving collinearity using vectors. Let's walk through an example. This is similar to example 27 in your notes. We need to prove that the points A, minus 1, 2, 3, B, 4, 0, minus 1, and C, 14, minus 4, minus 9, are collinear. First, we need to find the vectors A, B vector, and BC vector. Remember, to find the vector from point A to point B, we subtract the position vector of A from the position vector of B. So A, B vector is less than 4, minus 1, 0 to 2, 1 to 3 greater than, which simplifies to less than 5, minus 2, minus 4 greater than. Similarly, BC vector is a position vector of C minus the position vector of B. That's less than 14 to 4, 4 to 0, minus 9, minus 1 greater than, which simplifies to less than 10, minus 4, minus 8 greater than. Now for the second step, check for parallelism. Can we write one vector as a scalar multiple of the other? Let's look at BC vector. We can factor out a 2 from each component. This gives us 2 times the vector less than 5, minus 2, minus 4 greater than. Notice that the vector inside the parentheses is exactly our AB vector. So we have shown that BC vector equals 2 times AB vector. This proves that the vectors are parallel. Finally, we state our conclusion. Since BC vector is a scalar multiple of AB vector, they are parallel, and since they share the common point B, the points A, B, and C must be collinear. This completes the proof. Let's recap what we've covered. We started by defining parallel vectors as scalar multiples of each other. A equals k times B. We then learned how to find a unit vector in the direction of any vector by dividing it by its magnitude. This allows us to create vectors of any desired length and direction. Finally, we combined these ideas to prove collinearity. We showed that 3 points are collinear if the vectors between them are parallel and share a common point. You are now equipped to tackle problems involving parallelism, unit vectors, and collinearity, which are fundamental skills for the IBYA-HL curriculum. To solidify your understanding, here are 5 practice questions in the style of IB assessment. Pause the video and try them on your own before watching the solutions. Question 1. Determine if the vectors 3, -2, 4, and -6, 4, -8 are parallel. Question 2. Find the value of A such that the vectors A, 5, and 2, -10 are parallel. Question 3. Find a vector of length 5 units in the same direction as 2i dash 2j plus k. Question 4. The position vectors of points P, Q, and R are 1, 2, 3, 3, 5, 9, and 7, 11, 21 respectively. Show that P, Q, and R are collinear. And question 5. Point A is 2, 1, and point B is 3 units from A in the direction 4, -3. Find the coordinates of B. Take your time to work through these. The solutions will follow. Let's go through the solutions. First, question 1. We need to check if vector B is a scalar multiple of vector A. Let's see if we can find a k such that less than -6, 4, -8 greater than equals k times less than 3, -2, 4 greater than. Looking at the components, we can see that -6 is -2 times 3, 4 is -2 times -2, and -8 is -2 times 4. Since we found a consistent scalar, k equals -2, the vectors are indeed parallel. Now for question 2. For the vectors to be parallel, less than A, 5 greater than must equal k times less than 2, -10 greater than. From the second component, 5 equals -10k, so k equals -1/2. Substituting this into the first component, A equals -1/2 times 2, which gives A equals -1. Question 3. First, find the magnitude of the direction vector, which is the square root of 2 squared plus -2 squared plus 1 squared, or the square root of 9, which is 3. The unit vector is 1/3 times less than 2, -2, 1 greater than. To get a vector of length 5, we multiply by 5, giving us 5/3 times less than 2, -2, 1 greater than. Question 4. First, find the vectors PQ vector and QR vector. PQ vector is less than 2, 3, 6 greater than, and QR vector is less than 4, 6, 12 greater than. We can see that QR vector is 2 times PQ vector, so they are parallel. Since they share point Q, the points PQ and R are collinear. And finally, question 5. The direction vector less than 4, -3 greater than has a magnitude of 5. So the unit vector in that direction is 1/5 times less than 4, -3 greater than. Since B is 3 units from A, the vector AB vector is 3 times this unit vector, which is less than 12/5, -9/5 greater than. To find the coordinates of B, we add this vector to the position vector of A, less than 2, 1 greater than. This gives us less than 22/5 -4/5 greater than. I hope these examples and practice questions have helped you master the concepts of parallelism, unit vectors, and collinearity. Thank you for watching.